afternoon, everyone. Let's get started. I mentioned that we're going to pick up where we left off last time and code our instrumental variable regression, and I'll show you kind of a manual way of doing it and then kind of commonly how it's done. All right. So if you guys remember, last time we talked about this idea that we find an instrumental variable for our treatment variable, which is we're interested in the outcomes related to smoking as it relates to BMI in a causal sense. And we came up with this sort of cigarette tax idea. I showed you guys manually how you could do this with the two-stage least squares where you are regressing your treatment variable on your instrumental variable. That way, we can isolate the effect of the instrument, the change in your treatment as it relates to the instrument as the thing that's directly causing changes in your BMI. And so I did sort of forget to mention, so in this kind of idealized example, you can do it like this. But we actually have a whole bunch of other variables in our structural equation, right? And so in that case, you actually see, well, how do I know that when I put this particular thing back into here, that the changes related to my treatment are specifically related to the instrumental variable and not all these other things, right? And so you actually have to include the variables from your structural equation in here as well in the first stage. So I'm going to show you guys what that means in just a second. Okay, so you'll see what I'm talking about when we go to actually implement this in R. Okay, so first going to do this manually, then I'll show you kind of the normal way that this is done. I had uploaded a data set called ps6.txt, which we can import. It's tab separated, which is what I'm indicating here. So SEP means the type of separation. So like a comma separated file is CSVs with commas, and this data is organized by tabs. We have header equals true, so there are column names. I'm going to run this, and then I'm going to just go ahead and do a quick cleaning where I do complete.cases, which is going to drop any NAs in the data. Okay, and so if you want to see what this looks like, we can jump over here and view the data. And this is essentially all of the variables that I had shown in that particular example, right? So we have BMI, which is our outcome of interest, our response variable. And then we've got, where is it? Yes, whether or not you're a smoker here. And then cigarette tax, which will act as our instrumental variable. Okay. Okay, so if I were to just do this as an OLS, we might have something that looks like this. So BMI regressed on income, it's actually income squared and age squared. Female, pregnant, education, and smoke, which is our treatment variable that we're interested in. Okay, and here, if I run this example, we can see kind of the results here. And here, our treatment variable of interest, right? This is basically saying that if you smoke, your BMI would increase by 0.29 on average, but that's statistically sort of insignificant, okay? And so if we do it this way, this is kind of the problematic way, right? This is kind of the throw everything into the equation and see what happens. But we know, right, based off of our causal diagram, that we probably want to be structuring this in a slightly different way, right? We want to really be able to do a proper identification procedure on our treatment variable of interest. Okay, and so let's do our 2SLS example with the cigarette tax instrument. So I'm going to call this stage 1 model with cigarette tax. And I'm going to run my first stage, right, which is going to be, okay, who can help me out here? What am I running in my first stage? What am I regressing? Yeah, so smoke and cigarette tax. But actually, I also want to include all of the other variables from my structural equation, right, and all the other variables that we see in the OLS, because what you want to do is to try and remove the variation that those things are causing on your treatment variable, so that I can isolate the effect of the instrument on that variable, right? So cigarette tax plus income squared, age squared. Actually, I can just copy and paste this, right? All of this. Okay, so data equals BMI data. So I can run this, and you can actually take a look at your first stage results if you want. And so here, this is basically telling us that the larger the cigarette tax is, the less that you smoke, but it's not statistically significant. And one of the drawbacks of instrumental variable regression that I kind of mentioned before is that the strength of the instrument is related to how much of an effect the instrument has on your treatment variable, and oftentimes you are dealing with instruments that might be a little bit weak in some regards, and what happens is it dilutes the effect of your treatment on the outcome ultimately. And so that's a very common issue that we see in IV regressions. Uh, okay. Any questions at this point? Yeah.
Just to make sure I understand, the cigarette tax is your instrument variable because you're very sure that it's the only thing, like it only affects smoking, but not any other variable that has an effect on BMI.
Yes, that's right. So the instrument is something that affects the outcome variable only through the treatment and nothing else. And if it did go through anything else, then it would be an invalid instrument. Yeah.
Okay.
So would an example of that be like for EVs, maybe what you're measuring is like how many dollars of incentives people were distributed, for example, and then the instrument, I'm just curious if this can be applied to like a policy scenario.
Yeah. So instruments are very difficult to come up with, especially on the spot.
Okay.
But I can give you a different example related to transportation from one of the papers I published when I was doing my PhD. We were interested in how gas prices were affecting the amount of driving that people did in like the Northeast, like Pennsylvania and up. And there's a bunch of sort of endogeneity where things related to fuel prices are also like things that would probably affect the way that you might drive, right? So what are some examples of that? Like income, for example, right? And so you might be more sensitive to fuel prices, but it may also be related, your income is probably also related to like activities that you do, and so that may relate to how much you drive, right? And so we want to find something that can change gas prices and thereby affect how much you drive, but is only isolated to something that affects gas prices and not potentially all these other things that could affect how much you drive. So that the instrument that we devised was oil refinery shocks in the Gulf of Mexico. And when a hurricane comes through, you see a sudden change in production that causes refineries to shut down, and that affects oil prices kind of all throughout the country. But ostensibly, a hurricane in like the Gulf of Mexico doesn't really affect directly how someone drives, right? It's only affecting them through changes in fuel prices. So that's an example of like an instrument in that, yeah, in transportation,
Okay,
yeah.
thanks, that's helpful.
Okay, back to this thing. So this is kind of like the first half of the first stage, but then we also need to be able to get our predicted treatment, right? Which is the X hat that we were seeing in the second stage. And so to get that, all I need to do is I'm going to create a new variable called smoke IV sig tax. So this is going to be the predicted smoker values from the first stage. So we're going to take that model, stage 1, model sig tax, and that'll be my input into stage 2, where I run the main model, so BMI on all of this stuff, income squared plus age squared. And then here at the end, I'm going to add in the new predicted variable and we can see what happens. Yeah. So you can see here, this effect is actually quite a bit larger. Well, yeah. So this is saying that if you smoke, your BMI would be, higher on average by 137. This is like not a particularly robust example, but yeah, you can see the application of this. And yeah, so this is like a common econometrics technique. Oh, yes, importantly, I should mention, actually regarding the statistical significance. So these standard errors are wrong, okay? So the way that we calculate standard errors, you actually have to modify them because when you do the two-stage least squares estimation, you are actually affecting your standard errors in a certain way. And so there's a kind of complicated procedure on how to do that. I don't recommend we do it manually, just use the package. So all of this is kind of an illustration of what's happening behind the scenes in the two-stage least squares, so that you understand that when I do a two-stage, I'm regressing my treatment on my IV and other variables, and then I take the predicted in the second stage and put it in. But don't actually do this unless you want to modify the standard errors yourself. So the way that we implement this, so there's a package called AER that will do this for you. Cigarette tax to SLS model. And you can use a function called IVReg, which is instrumental variable regression. So the way that this is done is kind of like what we've been doing, except here we do smoke. So after you put in the treatment variable, which comes last, you do this vertical line and then put in the equation for your second stage. So income squared, for your first stage, plus sig tax. Yeah, so you'll see that when I run this, the coefficients will be the same as when I manually calculated it, but the standard errors will be, they should be slightly different. They should be actually slightly larger. Okay, any questions? So that's kind of the implementation of one way that you could do instrumental variable regression. And so kind of to back up and as a refresher, right, causal models require specific methods and procedures that we kind of covered in the last two lectures. The implementation of this is one thing, but I think particularly when we're talking about identification, you really the more important thing is being able to draw out and reason out your sort of causal diagrams, because that's kind of the foundation that any of this stuff even works, right? Yeah.
How do we interpret R squared?
Yeah. Actually, I don't know why that's like that. I will need to get back to you on that. I don't remember why it does this. You should be able to use like a modified form of an R squared. Yeah, I don't know why it reports it like this. I'll look into this. Get back to you. Yeah.
Why are we regressing on BMI instead of, like, in this case, instead of regressing on smoke, and smoke is the thing we want to, is smoke an explanatory variable we're looking into, or the response variable? I guess that would be
Yeah, so probably some of the confusion comes from the fact that we're regressing on it in the two-stage. So ultimately, BMI is our response variable. So this is our y. So in the second stage, we will be regressing on y, right? So the initial hypothesis is that the treatment effect, which is smoking, has some effect on BMI, right? So we want to understand how BMI changes. But the reason why we have a regression where we regress on smoking is to identify the effect of the instrumental variable so that we can make predictions about how this changes as it relates to this.
Okay.
Yeah. Okay, any other questions about inference in general? Great, because that's going to be the last that we think about inference, and we're going to pivot, and we're going to be sort of solidly in the prediction camp now, right? And so this is kind of the other, sort of the other end of the spectrum, and we're going to kind of start off simple and show the sort of evolution of how we get to sort of more and more complex sort of prediction methods. Okay, amongst kind of all of the things that we've been talking about, there is this sort of underlying assumption that we've kind of been working with through all of our regression models. And that is this idea of linearity, right? And so linear relationships between your variables and outcomes. And we kind of stretch that a little bit, right, when we try and modify the functional forms of things, like if I'm squaring things or logging things, right? You're doing transformations of your input data to try and turn them into linear fits so that you can still continue to run a linear model. And so fundamentally, we're doing all this, dancing around trying to keep things linear. And why do we do that? Yeah. Yeah, usually computationally faster, but yeah, more fundamentally, we do this so that we can have these nice interpretable coefficients, right? And those coefficients matter if I'm doing inference, right? I care about the relationship between my variables. But now, as we move more towards prediction, we can be like, okay, I don't care about the coefficients. I just care that my model gives me good estimates or good predictions, right? So let's think about how we can start to move away from linearity. Okay, so lecture 12. Okay, wait, hang on a second. Did I? Yes. I briefly freaked out that I wasn't recording, but I was. Okay. Beyond linearity. So as we move away from linear models, we lose interpretability, but we gain predictive power. And flexibility in fitting models. So we're going to talk about a whole bunch of different types of regressions today. So polynomial regressions. We're going to talk about step functions, regression splines, smoothing splines, local regression, and then general additive models. We'll see how far we get today in kind of this order. Okay, so we've talked about polynomial regressions before, right? So we have this thing where you have beta 0 plus beta 1 xi, and I can introduce sort of more model complexity by doing something like this. And I think we've seen examples of this before. And some of the drawbacks is this can become overly flexible and take on strange shapes near boundaries of X. Okay, so let's go ahead and draw up an example to use in R. And we're going to go straight into the deep end here. So we had made this example in the past. Of an artificial data set that we can fit our line through. And so I'm going to do the same thing, but now we're going to make it just extremely nonlinear. 0, 0.2. So it should look something like this. Oh. Okay, so I'm also going to add in the actual line here. So we can compare it against some of the examples that we're going to be doing. Okay, so this is what the data looks like. So there's a couple features of how this data looks, right? So the average values across X are increasing over time. It's got a sinusoidal waveform with amplitudes that are also changing in magnitude across values of X as well, right? Okay, so this is like a pretty nonlinear function. And I can, oh, what did I do here? Curve. I have to do times here. Okay, so, right, the nice thing of our artificial example is that we actually know the true value of the function, and so when I start to think about model fits, I have some basis of comparison, right, that ordinarily I might not have sort of access to. But okay, so the actual function looks like this in the blue line, and then any variation is just due to like the random error that I've introduced into the data. Okay, everyone good so far? So if we were just to start with a linear model, let's see here. Linear model, so that would just be lm y on x, and I can run that. And then I can, if I wanted to plot that, I could do so with AB line, linear model, color equals red. And I think this is where you can start to see maybe some of the shortcomings, right, in the linear model. So if I plot this, what do you guys think it'll look like? Yeah, straight line, exactly. So the linear model can tell us about the sort of overall slope change, right? But it's not capturing any of the sinusoidal shape, nor is it telling us about the magnitude of the amplitude of these waves. So let's try our first example, right, which is a polynomial model. Okay, and so I'm going to do y on, you can use this function called poly. So it'll add x squared, x cubed, x to the fourth, and so on. So it's adding degrees of freedom. It's adding flexibility that the model can use. And if I run this, and then for the purposes of plotting this, I'm going to predict across the range of data using that model. So I'm going to do from equals 0 to equals 5 in increments of 0.01. And now I can plot that line. So I'm going to do it as a new thing. Lines x equals sequence from equals 0 to equals 5, y equals 0.01, y equals polynomial predict 25, color equals red. Okay, So what I'm doing is I run my polynomial model with 25 polynomials. I predict across this range to get the fit, and then I draw it as a line. So that will look something like this. Okay. So you can see that when I use a polynomial regression, all of those polynomial terms that I get to just throw into the model are affording me flexibility, right? And here we can see the sort of average part is still captured, right? That's something that you're not going to lose because that's inherent in your, you still actually have your beta times x1 term, right? That isn't to a power. And then we can see that it's telling us correctly the kind of positions of the waveform, except for like here where you have some weird stuff happening. And then in general, the amplitudes are like roughly correct, but they're not all that accurate, right? So even with a pretty simple polynomial model, you're actually getting probably much better predictive outcomes than in your linear model. And then as far as the drawbacks that I was mentioning, kind of on the edges, and you can see it maybe a little bit over there, but particularly here, it's very pronounced, right? You can see that you get this type of artifact happening a lot with polynomial models. Okay, questions? So let's jump back and let's go to our next one. Okay, so our next example is the piecewise, also known as the segmented regression. So the way this works, so we'll start with our basic form. What I'm going to do is I'm actually going to split this up. So I'm going to say yi is equal to beta 0 plus beta 1 xi plus epsilon for any x's that are less than my breakpoint, and yi equals beta 2 plus beta 3 x1 plus epsilon I. Oh, okay, actually I forgot. Sorry, one last thing on the polynomial regression. How do I know how many polynomial terms to add? What do you guys think?
Test a whole bunch of them and pick which one has the best MSE.
And how do you do that?
Cross-validation?
Yeah, cross-validation, perfect. That's exactly right. So you can do cross-validation to figure out the number of correct polynomials. Okay, so in piecewise segmented regression, all you're saying is, okay, let me have different lines for different parts of my data, right? And so maybe in one part of it, I can have a line, I still have a straight line, and then another part, I'll have another straight line. And with those, I can have multiple segments across BPs, which are breakpoints. And so how would you guys imagine that I choose the number and location of the breakpoints? Yes?
Maybe if there is you set a certain threshold value and if it crosses over that threshold value, it becomes a new segment.
threshold value be?
Um,
I think you're closing in on the right idea. Yeah.
Cross-validation.
Cross-validation, yes. You could just test a whole bunch of different breakpoints and locations until you get one that gives you the best lowest mean squared error, right? And so, yeah. That is also, yeah. This will rapidly become a common theme if you guys aren't getting that yet, as we think about doing predictive models. Okay. So here I could just have a bunch of different segments and we can see what that looks like. This comes from a library called Segmented. So you'll have to install that if you don't already have it, which I don't know why you would. We use a function called Segmented where you input the original linear model and then I'm going to choose segments. Here, and then we'll do the same thing. We're going to do the prediction in order to be able to plot what this model is telling us. So, same as before. And let me just copy and paste that sequence part. Okay, and let's copy and paste our plot and then add in the new line. In fact, I'll just get this as well and change my Y. Okay, so here we're going to plot it. So yeah, I can just cut up my data into a whole bunch of segments, right? So that it's still technically in our linear model framework, but you just have many segments that allow me to fit many lines into, a nonlinear function or spread of data, and we can see it looks something like this, right? And in this particular case, actually the overall slope, the location of my waveforms, and the amplitude of those waveforms are all pretty accurate, right? But it doesn't do a good job at changing directions, right? And so you do have these almost like sort of discontinuous changes or very sudden changes in your slope, which don't reflect the curvature of our true function very well, right?
The function shows the breakpoints for you.
No, I just put in a crap load of breakpoints. Yeah. Okay, so what do you guys think? So, let me see. Actually, let me add this guy back in here, and we'll do it like a different color. And let me plot this one on top. Okay. Okay, so blue is our true, green is polynomial, and red is segmented. So who likes the red one and who likes the green one? So raise your hand for red, and raise your hand for green. Yeah, okay, so subjective, right, opinion on that, but you could actually go in and calculate, you know, your mean squared error term, right, and see which one gives actually better ones. Yeah, and that may help inform kind of which model is quote unquote better. Yeah.
I would figure it also depends on what you plan to do with the model, right? Because for example, with the segmented, if you're like doing some kinds of simulations or something, and then you're like close to these like turning points, maybe like there could like in a simulation like weird stuff could happen there because there's such a sudden change.
Yeah, although like in this particular case, like I don't know, you would be farther off, right, on the green one, even though it's rounder. So yeah. Yeah.
The segmented, so I guess in terms of interpreting those results, is that just like?
No. Okay, so like, right, so in the same way that like in a polynomial regression, right, you have like all these coefficients on polynomial terms, like, okay,
And it's not meaningful,
yeah, not that meaningful. Here you have the same, in the segmented one, technically you have your linear slope coefficient, right, but you have like a bunch of them now, and it's like, what are you gonna say about that, right? Yeah, so we're like that rapidly moving away from any ability to do kind of interpretation or inference of variable relationships.
Got it,
Yeah.
okay.
Okay.
Sorry, you mentioned that you set the breakpoints.
Yes.
How did you do that? Which part is that?
Yeah, sure. I'll show you. So the seg.z will tell you which variable that you're segmenting on. So x in this case. And then the psi input in the function tells us where you want to locate those breakpoints. And so here I just put breakpoints from 0.5 to 4.8 by every in increments of 0.2 on x. So every 1/5 of this, there's a new regression line being drawn.
So, even if we see it's pre-linear, it could potentially not be.
Yes. Yeah, like this part right here, that's probably like 2 actual different linear regressions, but it just so happens that. Okay. So you can see some of the strengths in these approaches, right? Which is in the polynomial, we have the ability to have like continuous changes in your slope, right? Which segmented does not have the ability to do that. But the segmented one, typically ends up kind of closer to your fit because of its ability to sort of rapidly change. And so there are pros and cons to both of these, but also nobody uses either of these, right? The reason why I'm kind of introducing this is to kind of show us the evolution in thinking to go from linear to these nonlinear. And in fact, the sort of more common way of thinking about this, or one step towards the way that people actually do these, is why not both, right? So we do something called a spline, which is a piecewise polynomial function. Right, note that you get flexibility from adding breakpoints, and you also get flexibility from adding polynomials. When you combine them, you have enough flexibility to make pretty much any functional form that you want. And so you actually become very worried about overfitting very rapidly with the combination of these two. And so you never really need to do more than 3 polynomials in a spline. And in fact, that cubic polynomials is the default way that a spline is constructed. Okay, do you have a question? Okay. So we're going to do splines, which are piecewise polynomial functions with a twist. Okay, so I'm always really bad at drawing these. So, kind of just bear with this kind of example here.
You're probably better than us.
Maybe. Okay. So let's say I fit a piecewise cubic, and I set this as my breakpoint. You might get a line that looks something like this, and then something like this. Okay. So this would be 2 cubic polynomial lines, regression line segments. Okay, and we have this issue here, which is this sudden break, right, in your lines. So we can do something slightly different. We can do what's known as a continuous piecewise cubic. So what this does is additional constraint that the lines must touch. Okay, so if I do this again, and I have my breakpoint here, but now they have to touch, it might look something like this. Where it tries to bring the points together. This is actually here. Let me.
Is there a slope constraint too?
No. Maybe it'll go like this. Yeah. So no constraint on the slope. But if you did add a constraint on the slope, then we could call that a cubic spline. So this is plus additional constraint that the lines must be smooth. So formally, this is first and second derivative are continuous at the breakpoint. Okay? And so that would make this look slightly different. This location here is what we would call a knot. So a knot is a breakpoint where you must enforce both these constraints that the lines have to touch and that the first and second derivative are continuous. And what that does is it will smooth it out so that, you know, you have a more normal looking curve. Okay, and so that actually so formally speaking, you're doing this thing where you have these what are known as basis transformations. If you all right, hang on. Okay, so these are called basis functions. So these are a family of functions or transformations that you can apply to a variable. So if you take a more rigorous statistics class, you can learn about what goes into these basis functions, what they're actually doing to x. But the main idea here is that they are helping us enforce these constraints. Yeah, and technically speaking, we're still in this kind of linear regression form, right? All we're doing is transformations of our x's. But now you're like, these betas don't really mean anything. They are relevant to some kind of weird transformed input data and aren't really interpretable in terms of like what it means to relate an input to an output, because you have this like intermediate basis function that's transforming the data. Okay, and so this is, you know, formally kind of how it's structured, but you don't need to worry about exactly what's going on here. So, as I mentioned, cubic splines are the most common. And what we do is we trade off the polynomial. So having lots of xn terms for knots. So if I were to draw some set of data, actually, can I like copy and paste a piece of this? I don't actually know how to do that. All right, whatever. I'll just draw the dots by hand.
Does your pen have like a button on it?
No, it's just I'll figure it out at some more convenient time than now. Okay, so If I have 0 knots, then your thing might look something like this. Maybe if you added 1 knot, maybe it looks like this. Then maybe I can add 2 knots. And then, I don't know. It might look a little bit different, right? And so you can kind of think of it as, with the polynomial regression, adding more polynomial terms is what allows you to get more flexibility into the model. That's how you're adding degrees of freedom. Here, it's the knots, right? Kind of in the same way that adding breakpoints will add degrees of freedom in the segmented. So 0 knots might look like this, 1 knot might look like this, 2 knots. Okay, and then if I had n knots, where n is equal to the number of data points, right, you can imagine that I have a lot of flexibility and my line might go kind of crazy. Kind of like what we talked about at the beginning of class, right, where we would have these crazy lines that jump in between a bunch of your data points, right? And so how do we know what's the right number of knots to include in our regression? Cross-validation, yes, you guys are getting it. Exactly. Okay, so let's implement this in R, and hopefully you guys will immediately see kind of the strength of this particular method compared to our 2 previous ones. It's really kind of taking the best of both worlds.
Can you repeat the definition of knots?
Yeah, so a knot is the same as a breakpoint, except it adds those 2 constraints, one of which is at the breakpoint the lines must touch, and the other is that it must be continuous, which means it kind of means that at that breakpoint the line has to be smooth, basically. Yeah, and so it's kind of an enhanced version of your breakpoints. All right. I'm going to save a little bit of time here. I'm going to copy and paste the big chunk of code and then just kind of walk through it. So we're essentially doing the same thing as before. And so again, this will be made available after class. So we're going to use a library called splines. So the basic way that I'm going to set this up, let me see if this is right. Yeah, right, okay. So just look at line 62. This is how we set up our cubic spline. We use our linear model, y regress on, and then we use BS. This is the basis function. So this is the thing that transforms our input data. So x, and then we're going to have knots. And I'm putting a knot on every x sequence from 0 to 5 by 1. So there's going to be a knot here, 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 and here. Okay? And then we're going to see kind of what happens. And so that I would characterize that as like a small number of knots for this data. And then we're gonna try again with cubic spline number 2. And so this is going to be doing the exact same thing, except I'm adding a knot at every half step increment. So it's gonna be, there's gonna be twice as many knots, one here, one here, one here, one here, one here, and so on. And then I'm gonna try and do it in increments of 0.3. And then 0.1, okay? And then I'm gonna plot them. So we run through all of these guys. Okay, so let's make this guy a little bit bigger. Okay, so this blue, there's gonna be a blue line, this is gonna be our first fit. Okay, and so if I have just looking at this slice here, and you added a sort of cubic function, my ability to kind of move with this curve in my cubic function, but then also make this line continuous, constrains it pretty heavily. So the best that it can really do is gonna end up looking something like this, right? So this looks kind of like your linear regression. And so let's see what happens as we continue to add flexibility into the model, right? And so, oh, I have, okay. Let me actually, I don't wanna, let me get rid of, I have a couple lines for the standard error, which is more for the notes. You don't need to worry about that. Okay, so now let's look at the next one. So if I go in every half step, you can see that there's a little bit more flexibility. And then we'll go again. So at every 0.3, now your knots are getting pretty, a lot closer. And at every 0.1, it'll look something like this. That green is kind of hard to see, isn't it? Let's do a darker green. There we go. Yeah. And you can see at increments of 0.01, it looks pretty good, right? And in fact, if I were to grab my original my true curve and plot it, we could see what that looks like. And let me plot that against just this guy here. So that's our cubic spline with knots at every 0.01. What did I say? Let's see. It's at every 0.1, sorry. Every 0.1. And you can see our true function, right, of our dotted blue line. It's basically right on top of it for the whole thing, right? So we've gone from sort of our linear model all the way to this ability to get like pretty dead on to, you know, what the true function is, through this sort of evolution of thinking about polynomial, segmented, combining them, and doing these splines. Okay, what do you guys think happens if I do this, if I increase the knots even more?
Different vibrations from next
Yeah, so let's see what happens here. Wait a minute. Oh, I thought it used to be different. Let's just add a 0 here. Why is that not working? Oh, it's because it's running. That's why. Maybe I shouldn't have done that twice. Yeah.
For this function now we already we have like a lot of data points, right? But how does it does this like kind of regression do if you have less data? Because if you don't have like as like dense the data point.
So there are certain types of like semi-parametric, non-parametric approaches that will do better and worse with like less or more data. I think generally speaking, regressions on small data sets, I think is you're just going to have a lot more error. And so it's not necessarily the case that these things won't work well, but if you were to plot the standard error of the fits, they might be a lot bigger when you have fewer data points. Yeah. There isn't necessarily a reason why the model becomes like intractable when you have like smaller data. Yeah.
I think you're predicting on the last one. It says predict for cubic spline 4 instead of 5. Maybe.
Oh. Thank you. I don't know how that happened. Okay. Let's see. Let me wait. I swear there used to be like a stop button around here. Hang on. Am I going crazy? Didn't there used to be a like halt task thing?
How do you know it's ready?
Is it a no? Okay, we're gonna. Oh, I don't know how to stop this without that button. Okay, hang on. Just quit out of here. Yeah, all right. We're gonna try this again. Okay, and I fixed that. All right, so we're just gonna, it's small enough that we can just run all this stuff. Great. Singular matrix. Okay. What if I do points? Sorry, I'm troubleshooting in the middle of class here. Wow, okay. All right. What ends up happening is you get these like crazy squiggly lines. I don't know why it's not working right now, because I have checked this before. Okay. Let's take a quick break, and then we'll continue talking about splines. And in the meantime, I will try and figure this out. There we go. I had too many zeros. All right, let's get back to it. I did fix our little problem, so you can actually see what it looks like. So for overfitting, if you have too many knots, then you start to get this like squiggly line effect, right? And so this is classic example of overfitting, and we can avoid this, right, by doing a cross validation to get actually the appropriate smoothness of our spline. But yeah, this is what happens when you add too many knots. Okay. back to the notes. So cubic splines, pretty useful tool, but also something that's people don't actually use. There's one last modification that we're going to talk about with these splines to get us to the point that we're talking about where this actually is a little bit more common for certain applications, right? And so that thing is a natural spline. So splines can have high variance in outer ranges of predictors. Okay? And that has to do with the fact that polynomial models tend to have that crazy thing happening at the sort of peripheries. And that is an artifact that is still yet carried over into splines. Even with just cubic, you can have that artifact kind of showing up. And oftentimes because of that, the standard errors around your model fit get inflated by quite a bit at sort of the boundaries, or they can be inflated quite a bit. And so a natural spline adds constraints so that the function is linear at the boundaries. So if I have, some data set where I have some kind of fit like here, your cubic spline, if you look at the sort of standard errors of your cubic spline, it tends to kind of explode at the edges, whereas with the natural spline, it might be a little bit more realistic in terms of those. And so natural splines kind of as a continued progression on how we're talking about the sort of evolution of these things go. If you're thinking about doing some kind of spline approach, the natural spline is definitely more preferred than your cubic spline approach. Okay? And it's a pretty similar setup in R. So instead of BS basis function, it uses the natural spline basis function. So NS, and all you need to do is specify the degrees of freedom, right? So degrees of freedom are related to the number of knots that you can have. And so the larger the number of knots, the more flexible it is. And the fewer the degrees of freedom, the fewer number of knots, then the less flexible. So we do kind of the same exercise as before. I'm going to do natural splines, one with 10 degrees, one with 15 degrees, and one with 30 degrees of freedom. And we can see what those look like. That's with 10. Get rid of this guy. This is with 15 degrees of freedom. And this is with 30 degrees of freedom. Okay? So we can see once we get up to about 30, we're getting kind of this nice smooth thing, and that's going to approximate our true function pretty nicely. Okay. And to show you guys the difference between the cubic and the natural splines, there's our true. Let me see here. Yeah, so it might be kind of hard to see, right? But the standard error kind of right at the boundary is like this wide for my cubic spline, and it's about that wide for my natural spline.
The red dot.
Yeah, so the red is the natural and the blue is the cubic. And similar here, the blue is like this and the red is like that. It's, yeah, maybe, yeah, I guess at the end of the day, like, whether or not this really matters for you, you know, most people consider and have done the work to make the, to figure out how to, you know, deal with this particular issue. So, yeah, natural spline is kind of the preferred method here. Yeah.
What's an example of a research question that you would apply like something like this to?
Yeah, so if you had data that is like highly nonlinear and you wanted to do a really good job of, you know, predicting that outcomes related to that data set, then spline-based approaches are very, very powerful at being able to fit to any sort of functional form. And so this type of thing is in some ways outdated, in the sense that like a lot of modern day predictive stuff is more kind of pure machine learning where you're doing like neural network type things. But the basis for some of the like transformations and thinking on how you deal with functional forms in neural networks like comes a little bit from this. And so, yeah, this is, it's still used, not so frequently, but if you really, really just care about predictive outcomes and you have like a really, really sort of nonlinear sets of data, this can do a pretty good job at dealing with that. Yeah.
In what condition would you care about like the end boundaries when to use basic or
I don't know. To be honest, like I learned about this stuff in some classes when I was in grad school, and you know, to me, the functional difference between a cubic spline and a natural spline isn't so big in the sense that like I haven't really seen a real good example of why I would really want to care about this versus this. But it's, to me, it's more like, well, you know, it's natural spline is almost strictly better than a cubic spline, so why not just, you know, use that, right?
What happens if your data has more than 2 variables?
Yes. So you can still do this. Let me see here. But there's actually a slightly different approach to talk about with if you're talking about things where there isn't as much interdependence between your variables, then you can still do this. And actually, let me back up a second. I've been talking about the application of splines to problems as a totally like a research problem that uses purely splines, right? But actually there are applications, common applications of splines as part of like a different modeling approach. We're gonna talk about it either. We probably don't have enough time today, so maybe at the start of next class I'll talk about it. But actually, we can incorporate this kind of thinking actually into even linear modeling approaches, even as a way to test the functional form. So I'm going to talk about that more in a second, and then that's actually an example of an appropriate and common use of splines in applications, even in inference. But you guys will see what I'm talking about in a moment, or next Monday. Yeah. So yeah, there actually is a pretty common use of this in kind of a slightly different context. Okay. Let's see. We'll have time for one more spline thing. Okay, so smoothing splines. Also known as my favorite splines. Okay, so general regression now looks just slightly different. We have yi minus g of xi squared. G of xi is the spline cubic function. So spline cubic function. So this is the thing that constrains your first and second derivatives to be continuous. Okay. So let's suppose you do have a knot. Wrong one. Not at every point. Okay? So if I had some kind of knot and or if I had a data set and I decided to include a knot at every possible point, like this, that will perfectly minimize my RSS, right? I will have no error because I'm now afforded the flexibility to essentially pass my line through every single point, right? And so I could get, some crazy thing, right? So this perfectly minimizes RSS, but you have overfitting. Our classic problem, right? Okay, so let's do something creative here. So let's shrink the second derivative. So now I'm going to have a new optimization function, which is going to look a lot like the other one. So it'll look like this, just like before, but now I'm going to add this thing over here. And so this little guy is a penalty function. And this lambda is our tuning parameter. Okay, what does this look like to you guys?
Yeah, ridge and muscle.
Yes, this is just like the ridge regression. What is the second derivative? What does that do? Let's say, yeah,
It's the changes in the slope.
yes. So if the second derivative of my basis function is really small, what does that tell me about how much the slope can change? Not much, right? And so that forces your line to be flatter, right? If your second derivative is really big, then you can change directions in your slope very quickly, okay? So very similar to the concept in the ridge regression, this process, so this penalizes the function by encouraging smoothness. Okay, so even if I have a knot at every single point, okay, if I have a low value of lambda, so a small tuning parameter, then you can kind of do whatever you want, right? But if I have a high lambda, large tuning parameter, then you may be less able to kind of rapidly change the slope, right? And so this is very much akin to what we were doing with the ridge regression. Here, it's kind of nice where now I don't need to think about the number of knots to put into my regression. I just put them all in, and all I have to do is change a single parameter, right, which is my lambda, yeah.
Question. So this calls probably again for cross-validation.
Yeah, how do you choose your lambda? Cross-validation, yes.
But my question is, if you do, like, for example, the k-fold cross-validation,
Yes.
every time you get a slightly different result, right?
Yes.
Like, are there any rules, like how to choose the case or the differences, like the changes in the outcome are smaller?
No, that will depend on the context of the problem, right? Because the variation will naturally be larger depending on the variation in the data. So it's data dependent.
But is there anything that's done, or do people just do one cross-validation, just take the result, or like how do you deal with that?
Yeah, so actually they'll run the cross-validation many
And
times.
then it converges.
Yeah, yes. So they do converge.
In the assignment, do we have to do that?
No, you don't need to do that. Yeah. Okay. So our last ones of the day is the smoothing splines. Yeah. So you have your x, your y, and then s bar is the tuning parameter. So the larger it is, the flatter it is, and the smaller it is, the more flexible it is. Okay, so here we go. So here is with a large tuning parameter, and it's almost just a straight line. And then we're going to incrementally decrease the size of our tuning parameter. Wait,
Is it the other one?
no, that's right.
How many?
Low, I always get this mixed up. Low lambda, yeah, it's more flexible, right? Because you're reducing the size of the penalty on my ability to be flexible.
Because the lambda knots the tuning, if you have a low lambda, then you're not tuning it that much, so that's why you have.
Yeah,
Oh,
yeah,
no, that's at
exactly.
every point, right?
Every point,
Okay.
yeah. So now we don't need to think about knots, right? This one has 1,000 knots because there's 1,000 points. That's why I like this one, because you just need, all you need to do, you know, if you're really doing natural splines and cubic splines, you know, you would be thinking about number of knots and position of knots, right? And so it gets a little bit, I mean, there are ways to automate that, obviously, but here you literally just, there's one parameter and that's it. So I tend to think this is kind of the cleanest. Okay, so let it be more flexible, let it be even more flexible, and right around green, I think we're doing a pretty good job already. And then orange, okay, I don't know if you guys can see, but once we're getting to orange, we're starting to get these like little perturbations. Yeah, and so even at orange, I would argue you're starting to overfit your true function.
Would it be appropriate to like use R squared here to see which one is good in between green and orange?
No.
Because
Because your R squared will always improve when you introduce more flexibility. This is our classic overfitting thing.
What parameter would you use?
I don't know, what parameters would you guys use? Yeah, out of sample MSE. Yeah. Yeah, and then black, right? And you can see that kind of most pronounced here. You can see it starting to squiggle, right? Very kind of noticeable. And so, yeah, and technically the black would have the highest R squared out of all of these. But we would argue that it's overfitting. Yeah.
Shouldn't the black if it has as many like no knots and like they're like 1,000 knots, shouldn't it have hit all the data points with 0 lambda?
So
Because if it has like it's all like it has as many knots as data points, it can technically hit all them and if the
0 is not the lowest you can go.
if it's 0 then there's no penalty, right? Because you multiply with the lambda.
Yeah, but you can actually, there's still constraints, right? There's constraints on how much it can, there's still the pieces in G of X that you have to like line up the thing, and so there's like these soft constraints. Also, S par is actually a little bit more complicated than the flat out like tuning parameter. There's some extra stuff in there. You'd have to read about it. Yeah, so I can actually go to like promote more flexibility by going even like negative. Actually, I wonder how crazy I can get it. Okay, 100. Let's try it. At a certain point, at a certain point, the like inherent constraints will override kind of what's in the. But you're like well into the area of like overfitting by that point. Yeah. Okay. So you guys have learned about splines. Yeah.
Just a quick question, computationally, you were working with a lot of data, is there like if you happen to need to constrain like how much memory you're using in space, is there a big difference between the?
So that's actually one of the big benefits of splines is that they're computationally very efficient. Yeah, so you could do this with a very large data set. We're going to talk about local regressions later, on, I guess today's Wednesday, right? So on Monday, we'll talk about local regressions, and they'll do similar things and have similar characteristics of kernels, even though they're done extremely differently. But one of the drawbacks with like kernel regressions and those sorts of approaches, or local regression approaches, is that computationally those tend to be a little bit more intensive. And so splines actually become favorable in some applications because of their computational efficiency.
Even if you have an audit every.
Yeah. The math behind the splines is like very straightforward. So yeah, they're computationally efficient.
Thanks.
Yeah. Yep. Okay. Great. So that's it for today. Next time we'll start off showing kind of the application of these splines in a broader sense, so you can see how you guys could use them. Yeah. And otherwise, homeworks are is it this week or next? Next Wednesday. Next Wednesday.
One quick question about the project.